Thank you. Okay, so if you're having issues with installing water gems, I'd just suggest that probably it's easiest at this point to use the lab computer since it's installed on them. That assignment, the lab assignment that goes with Water Gems 1 is due on Tuesday in lab. And we'll be back to Group A at 2 o'clock, Group B at 3 o'clock this coming Tuesday. Also, same day, homework 3B is due. All right. What we're going to start off with today is a couple of tips to help you on the homework assignment, and then we'll get back to that example we were working on last time in class when we ran out of time and had to conclude. So first of all, some key ideas on problem. Was this recording? All right, yep. Some key ideas on problem 323. It asks you, everybody's having all sorts of trouble with the new iOS, huh? Just think, it's become self-aware. It does what it wants now. All right, this is asking you what force is required from the bolts to hold the dome in place. So what's happening is there's water inside of here and it's under pressure. If these bolts weren't here, then what would happen is the water would be leaking out. It would just basically lift the dome up and water would leak underneath. And so the bolts are pulling down on the dome in order to seal it so that there isn't any dripping. And what we know, the given information is that the dome and the pipe together weigh 6 kilonewtons, that this dimension L is 80 centimeters. And so since this is a dome, what that means is that there's a circle here, and the radius of the circle is 2L. So it's 160 centimeters in radius, that circle. And we know the inner diameter, and from that are able to calculate the volume of water that's there. In the back of your book, it gives you formulas for the volume of a sphere, for example. And if you cut that in half, then you can find the volume of water that's here, and you can calculate the volume of water that's in the tube. And from knowing the volume, calculate the weight of the water that's there. And the reason why you need to know the weight of the water is that you're going to be doing a force balance in the z direction, so meaning up and down. And let's think about what are the forces that are in play here. There's first of all, the force of the bolts, pulling it down. We'll think about that. So the bolts are pulling down on the dome, so we have to calculate that force. This is going to be the unknown. The weight of the water is acting down. That's the weight of the water that's inside the dome and also the weight of the water that's in that tube. And then the weight of the dome itself, which is given as 6 kilonewtons. Now this last force is it's a hydrostatic pressure that's actually pushing up on the water. Since the water is pushing down on whatever, if this is a table or maybe a concrete pad or something, the water is pushing down on it. That means that the surface is pushing up on the water with an equal and opposite force in order to hold it in place. And so you can find the pressure of the water at the bottom of that dome just by using the hydrostatic equation, because here over on the left side it tells you the distance of the water down to the bottom. And so with the hydrostatic equation and knowing it's water, you can just assume that the unit weight is 9810 newtons per cubic meter. You can find the pressure at the bottom of the dome, previously having calculated the area of the bottom, and that's acting as a force that is up. And so you'll have all of these terms except for the force of the bolts. The real kind of secret tricky thing here is recognizing that that surface is pushing up as though it's an external force on the system. The system itself that you're considering is the water and the dome. And so that there's a force pushing up on the system from the surface that the system is in contact with. Those are some key ideas for problem 23. Any questions about that one? As you draw a sketch of the system, be sure to indicate the direction of the force. You know, that the water is acting down, the bolts are acting down on the system, that the table or the concrete pad is acting up on the system, and so on. Okay, the other problem I wanted to give you some specific guidance on was problem 32. And it tells you to calculate H based on not only, H is given, so I don't remember what the unknown in this problem was. Anybody have the book handy? Let me just take a quick look, because I got to remind myself what it asked you to find. 32. Pressure at the pipe. Okay, so find the pressure at A. You can't just use the hydrostatic equation, though, because the tube is so small. Remember that the capillary forces pull water up. And we had an example earlier in the semester where we had some water tank and a very thin tube, and we calculated what was the rise as the surface tension force, the force due to surface tension, pulled the water up. And there was an equilibrium between the weight of the water above the water line in the glass tube and the surface tension forces. And you remember from surface tension forces, it was surface tension constant times some length. And in the case of a circular tube, it is the circumference around that glass tube. So here you have part of H is due to surface tension forces. And if you look at the pressure distribution inside of this tube, the pressure, it's open to the atmosphere. And so the pressure is atmospheric, but then as soon as you go down just a little bit, just a fraction of a millimeter, it's actually a negative pressure because of the capillary effect. And so you have to go down a little ways before you get to 0, and then you go down and the pressure is increasing. And so you've got 100 millimeters of H. What you need to do is find out how much of that 100 millimeters is actually due to the capillary effect of the glass tube is sucking the water up out of this reservoir, some amount of it. So in the previous example that we worked in class, we found the relationship between delta H and the surface tension forces. And so for the inside glass diameter that they're giving you of 0.5 millimeters, you need to find out of this 100 millimeters of total H, how much of that is capillary rise, and then the rest of it you can apply into the hydrostatic equation.
The way you've got this wrong, the pipe actually penetrates the surface, and this one is much shorter.
Here?
Yes.
Well, think of it as a reservoir, and here's the pipe. So the pipe is connected to a reservoir of water. And so part of that rise is the glass tube is sucking up water from the reservoir. Part of it is because the liquid is pressurized at A. That's part of the reason why the water is rising up in the tube. But the other part of it is because of capillary forces. Now the capillary... The glass tube, remember there's an attractive force between the water and the glass tube, and so the water wants to maximize its contact with the glass tube, and so it's going to rise as high as it possibly can to have as much surface contact between the glass and the water. So that's sort of the trick of problem 32. One last thing I'll remind you of is the definition of piezometric pressure, and we worked an example with an inclined pipe, and we found the difference in piezometric pressure between one location and the other. And we've talked about head when we were talking about how if you have a pipe and you put a hole in the pipe, the water will spray all over the place. But then if you had another little tube that was just rising, that you could have the water level rise to a certain elevation inside of the piezometer that is an indicator of what's the pressure in the pipe here. And so we called this head, how much the water rises up out of a tube. We refer to that as head. Well, we can have piezometric pressure. That's the definition of piezometric pressure. And there's also piezometric head, denoted by H. And I just wanted to emphasize and point out to you that if you have a homework problem where it asks you to calculate the piezometric head, then this is the formula that you can use. And so for a difference in piezometric head, the delta H that you measure, the deflection in the manometer fluid, delta H, allows you to find the difference in the piezometric head. And so here's the formula for that, how you find the difference in head between 1 and 2 when you've got a piezometer. It's going to be the ratio of the manometer fluid and the fluid that's flowing through the pipe minus 1. Just in case that might come in handy for your homework assignment. All right, so this is where we left off last time. We were partway through this example where we have an elliptical gate covering the opening of a pipe. The water forces are pushing down on that gate, keeping it closed, sealing it up. And what we had found was the depth to the centroid was 10 meters. We're working on part 1. We had depth to centroid is 10 meters, and that is the 8 meters to the edge of the hinge and then another 2 meters down to the middle of that pipe, because the vertical component of the ellipse is 4 meters. Okay, so that gives us the depth of the centroid, and the force is going to be 10 meters times 9810 newtons per meter cubed. It's then times the area. The area of the ellipse we had found to be, the formula is pi AB, and that was 15.708 meters squared. 15.708 meters squared. Okay, the force is 1.541 meganewtons. And in part 2, we have the formula of YCP. It's y bar plus I divided by y bar A. And to find the y bar, we'd looked at similar triangles where we've got a 3, 4, 5 triangle, and that allowed us to find that if the vertical component is 10 meters, then y bar will be 12.5 meters. Okay, so also with the ellipse, we could find the area moment of inertia is pi AB cubed divided by 4. So that's pi times 2 meters times 2.5 meters cubed divided by 4. The ellipse has an area moment of inertia 24.544 meters to the 4th. Now finally, what I'd suggested right when we left off was we can find YCP, or more usefully, we could find YCP minus y bar. Because ultimately what we want to know is the force required to open the gate. And so let me illustrate why it's more useful for us to find the difference between y bar and YCP. Here's our tank, and there's some pipe going in, and here's the gate on it. Okay, now YCP and y bar, here's the water surface, and so we have to extend this out to where the water surface would be, and from the centroid to the water surface, that's y bar, is this distance. Okay, so we have the formula for YCP, and the hydrostatic force is below the centroid, the location that it's applied. So we can find YCP from the water, all the way from the water surface down to where that is. So from here is going to be YCP up to the water surface down to the location of the force. But that's not a very useful point of reference all the way up to the water surface. Ultimately, we're going to be summing the moments about that hinge, and so why don't we keep our location references relative to the plate that's covering the opening on that pipe rather than using the water surface as our location reference? Because what we're going to eventually be doing in this problem is we're going to be saying we've got to find what is the force F that's required to open it when we've got a hydrostatic force. So force hydrostatic is down here, and we don't know exactly what the distance is yet. But we know that it's somewhere below the centroid. So here's the centroid, and we know that the hydrostatic force is a little bit lower than the centroid. So what this will tell us, what YCP minus Y bar is going to tell us how far that force is from the centroid. So this distance right here, that gap distance is YCP minus Y bar. How that YCP minus Y bar is distance from centroid to center of pressure. And of course, the center of pressure is where the hydrostatic force is actually applied. The equivalent hydrostatic force is located at the center of pressure. Okay, so let's go do that calculation. We will have the I, which is 24.544 meters to the fourth, and the Y bar, which we'd calculated as 12.5 meters, and the area 15.708 meters squared, 0.125 meters. So the distance from the centroid down to where the force is located is 0.125 meters. So when I do the moment analysis, I'm going to have the 1.54 meganewtons is the magnitude of the force. Okay, so we're going to want to pull the gate at F. And here we've got previously calculated 1.541 meganewtons. And what is the distance from the hinge down to the location of that force? It's just going to be from here to the centroid plus the 0.125 meters. And so the total length of it is 5 meters. So from the hinge to the centroid is 2.5, and then we have to go the additional 0.125. And so this distance is going to be 2.625 meters. And then, of course, F, its moment distance is 5 meters. So we've got F acting at 5 meters, and that will be equivalent to 1.541 meganewtons acting at a distance of 2.625 meters. So F is 0.809 meganewtons. That's the force required to begin to open the gate. Any questions about that one?
Yeah, real quick, I forgot how you got the 10 meters again.
Okay. It's because the vertical component of that gate, the depth to the centroid, is going to be the 8 to the hinge, and then vertically, from here to the bottom, the distance is 4 meters. And so just it's an extra 2 meters to get to the centroid.
We weren't using
No, we were just using the triangle, looking at it as a, the vertical component of that face is 4 meters. Other questions? What if we have a plate that is oriented horizontally in the water? We've already looked at a vertically inclined plate, a plate that's at an angle, and now we've got a plate that's flat essentially, but it's under the water. So what if we want to find what's the hydrostatic force acting on top of the plate? There's two ways that we can solve this. First, we'll just start by looking at what's the pressure at a certain depth. So this example, the plate is at a depth of 5 meters. We need to find what's the water pressure at that depth. And then use that to find the force. So first of all, delta H is 5 meters. We know that the formula for force is the pressure at the centroid times the area. So the centroid of this is at the middle of the rectangle. This is a 2 by 3 rectangle. So the centroid is here, and it's at a depth of 5 meters. So we're going to find the pressure at the centroid, multiply it by the area of the face of that plate. So it is going to be delta H times gamma to get the pressure at the centroid, then times the area. That is 5 meters of depth, 9810 newtons per meter cubed is the unit weight, and then the area of it is 6 square meters. So that force is 294,300 newtons. And the location is at the centroid. Now, of course, there's also a hydrostatic force acting on the bottom side of the plate, but we're just asking about what is the force acting on the top of the plate. The alternate way to do that, to find that force, the hydrostatic force, is consider what is the weight of the water that's above the plate. And so weight of water. And the way that we do that is we just assume, we've got some water, and underneath the surface here is our plate, and we're going to find out what is the volume of water that's above that plate. So if we go up to the surface, how much water is inside this theoretical box? Okay, weight of water will be the unit weight times the volume. And the unit weight is 9810 newtons per meter cubed. And the volume here is 2 meters by 3 meters by 5 meters. That's a total of 30 cubic meters. That's the volume above the plate. And the weight of the water is 294,300 newtons. Now that only works if it's a horizontally oriented plate. But that's going to be an important part of solving forces on curved surfaces, which is where we're headed. We've just been talking about flat plates so far. A flat plate that's vertically oriented, one that's horizontally oriented, or at an angle, any angle. We've got this formula for finding it that includes, you find where is the centroid, then you find the pressure at the centroid. That's how you get the magnitude of the force. And then the location of the force, you find the center of pressure. And the formula for the center of the pressure location is y bar plus I divided by y bar A. So that's the whole process we've gone through for flat plates. But where we're headed next is What if you've got a curved surface? How do you find the hydrostatic forces on a curved surface? And part of that procedure we're going to use takes into account looking up what's the weight of water above a surface. So this is kind of like a sneak preview of what we're going to head to for the rest of today's class period. Any questions so far? Yeah.
So with the method you just used, does it have to be a square plate, or can it be some sort of like ellipse, or?
It could be any shape, as long as it's flat. Flat and horizontal, yeah. The weight of the water. That idea that the force, the hydrostatic force, is equal to the weight of the water. It works for a flat surface that's oriented horizontally. Before we talk about curved surfaces, we have to talk about the idea of a projection. An orthographic projection is a 2D representation of an object that exists in 3 dimensions. For example, think about if you were trying to make shadow animals using your hands. The shadow itself is flat. It's a flat representation of a 3-dimensional object that's made by putting something between the light that's shining and the surface that the projection is going to go onto. And here's a more sophisticated representation of a projection. Think about if you had an X-ray of an object, what that X-ray would look like. This object has some curves to it that are just going to exist as a flat rectangle. The projection sees that angled surface just as a vertical projection. And so the reason why I bring it up is that we're going to have to analyze curved surfaces like this. If we want to find out what are the hydrostatic forces on a curved surface, we're going to have to consider its projection. A curve like that will have a flat projection. And we break up the curved surface into a vertical and a horizontal component. And then we can find the force components, vertical and horizontal, and combine them together in order to find the overall hydrostatic force. And so let's just think about if there was water, and it may be some sort of a tank that has a flat edge here and a flat edge at the bottom, and it's connected by an angled plate. So what is the shape of this curve? What does it look like to you? It looks like a quarter circle, right? Some of the important questions that you should ask is, how deep is it? So you'd want to know the distance between the water surface and where the curve begins. That's something that's important for you to know. Also, you'd want to know the dimensions of where does it intersect the flat surfaces. So in other words, what's the radius of the curve? How big is that curve? So let's just say that we define some of the geometry that was just pointed out as being important on the previous slide here. So let's say that we have a radius of curvature of 2 meters. So this is a quarter circle from A to B, and the depth from the water surface down to where the curve begins at B is 4 meters. It's a 4-meter depth to the beginning of that quarter circle curve. Radius of curvature, 2 meter. And we've got this broken up into a couple of components. We've got it looks like a pie-shaped wedge here, A, B, C. And then above it is a rectangle, B, C, D, E. So we're breaking it up into pieces because what we're going to do is find the weight of the water of each of those pieces. Now, the next piece of information that we've got is that this is a 1 meter into the paper. And so this is an angled plate here, AB is an angled plate, and it's flat 1 meter into the paper. So it does have depth of 1 meter. So it was maybe like a flat metal piece that was pushed was rolled out into a quarter circle, and its depth into the page is 1 meter. So we're going to have to calculate the force components in order to find the overall hydrostatic force. And this force F here is the force that would be required to hold the system steady. And so it is the force that will counter the weight of the water from element A, B, C. And there's water weight above that element that accumulates on the curved surface. And then there's going to be a hydrostatic force component that we also take into account by considering the vertical projection of that curve. So we'll go through each of those steps one at a time. First of all, finding the force, the vertical forces acting above BC. So that's going to be like a rectangle of water, a rectangular box. We're going to find the weight of the water, and then we're going to find the weight of the water of the quarter circle shaped element, and then we'll consider the vertical projection of the curved surface. Feel free to stop me if you've got questions at any point. This is important. This is an important example because it illustrates the procedure that we can use for any shape. It's not just going to be like a curved flat plate, like this. Any kind of curved surface you can use the same procedure on. So first of all, we're going to find the vertical forces. Let's see. All right, yeah. Here's the steps that we'll go through. Find F sub h. Now, the vertical projection is going to basically just be 2 meters high, and it will have a width of 1 meter because it's given at the top there that it goes 1 meter into the paper. So this curved surface, we're just looking at the vertical component of it, and we're going to find the hydrostatic forces on that theoretical vertical element. And the force hydrostatic will be delta H times gamma times A. So we have to find, the centroid will be at a depth of 1 meter from C down to the centroid, and then an additional 4 meters from C up to the water surface. So delta H is going to be 5 meters, 9810 newtons per meter cubed is the unit weight of the fluid, and the area is 2 meters squared. That's the area of the vertical projection of the curved surface. And that gives us that the hydrostatic force is 98.1 kilonewtons. All right. Next, we want to find F sub V. Okay. F sub V is equal to the weight of the water inside of that volume. It will be the unit weight times the volume of element B, C, D, E. So 9810 newtons per cubic meter. And then the volume is going to be 2 meters times 4 meters times 1 meter. So 2 meters is this dimension from B to C. 4 meters is from C up to D. And then 1 meter is the depth into the page.
First calculation, where's the 5 meters from?
5 meters is from the centroid of the projected shape up to the surface. Remember that if we had think about if you had a flashlight over here and you were shining a light, what would the shadow look like of this curved surface? It would just be a rectangle because it goes 1 meter into the page and it has a height of 2 meters. And so what we wanted to do is we wanted to find from the centroid of the vertical projection up to the surface, that's 5 meters. See 2 meters up at the top, DE. that means that BC is 2 meters, and then if you trace it, it goes all the way down because it's a quarter circle. Yep. They're usually rectangles or circles. Nope. 78.48 kilonewtons. So that is the weight of the water in element B, C, D, E. Okay, next we want to find the weight of the water in element A, B, C. So that is going to be gamma times volume in A, B, C. The formula there will be gamma times 1/4 pi r squared times 1 meter, which is the depth into the page. So 9810 newtons per meter cubed, and 1/4 times pi. 2 meters is the radius of curvature squared, and then 1 meter is the depth into the page. So all of that together gives us that the weight of element of that pi-shaped element is 30.819 kilonewtons. So if we add up all of the horizontal forces, we want to find the components of the force that has to be added. So what is the horizontal component of this F, and what is the vertical component of F? So we can say f of x, f of y. The horizontal component is simply that f of x is equal to f of h. So it's 98.1 kilonewtons. 98.1 kilonewtons is how much we have to push on this gate in the left direction to resist the hydrostatic forces. And think, in reality, there's all this pressure acting on the gate. And the pressure is deeper at the bottom, and its direction is changing because of the curvature. But all of that is taken into account when we break it up into the pieces like we had. So the force required towards the left is 98.1, and the vertical component, we've got the vertical component of F is going to be the 78.48 kilonewtons plus the 30.819 kilonewtons. So the total is 109.299 kilonewtons. 109.299 kilonewtons. So the overall magnitude of F, of course, we're going to find just by adding the squares and taking the square root. So F is the square root of 98.1 kilonewtons squared plus 109.299 kilonewtons squared it is 146.87 kilonewtons. So that's the magnitude of F required to hold the system steady. To make sure that gate doesn't come just popping off, F should be 146.87 kilonewtons. Last thing it's asking for is the line of action. And what that means is, where are these forces located? In order to find the line of action, we have to find where each of the forces is centered. Each of the component forces is centered. And so some of it is obvious, like the location of this force that we're calling F sub V. And it's obviously going to be just halfway between B and C. What about this force W? Will it be exactly in the half? Will it be in the middle between B and C? Will it be shifted to the left, shifted to the right? Okay, wherever the center of area is. Very good. For a quarter circle. Probably it's going to be shifted over a little towards the left, because if you look, there's this piece that's missing over here. I almost marked up the screen again. So it's shifted a little bit halfway towards the left. And then the line of action for the horizontal force, to find that, we use our approach of calculating YCP, same as we have for any other vertically oriented plate. We treat it as though it's a flat plate. We're finding the projection of a curved surface in order to find not only the magnitude of the force, but the location. So let's start off by finding the horizontal line of action. Okay, the horizontal line of action, we're going to use the formula for YCP is y bar plus I divided by y bar A. And here, y bar is the same as delta H because it's a vertically oriented pretend surface. Remember, a projection is like a make-believe surface. We're taking just the vertical projection of that curved surface there. So it's a curved surface, but its projection is from A to C. It's 2 meters tall and 1 meter into the page. And so the depth to the centroid is 5 meters. So y bar is equal to delta H, and that's equal to 5 meters. And the area moment of inertia for something that is 1 meter by 2 meters, AB cubed divided by 12. How do you know which one is A and which one is B? Just think that the vertical one is what's most important for area moment of inertia, so that's the one that you're cubing. So A is 1 meter, B is 2 meters. We cube B divided by 12. So the area moment of inertia for this rectangle is 0.6667 meters to the fourth. That gives us a YCP of equal to 5.0667 meters. That's the distance from the surface down to where the hydrostatic force is located. So it's a little bit lower than the centroid. The centroid was at 5, and the center of pressure is at 5.0667. It's not much further below the centroid in this case because the plate's pretty deeply submerged. The vertical line of action. So we've done the horizontal line of action. Let's consider the vertical line of action. All right. We've got F sub V acting halfway between B and C. So if we represent that quarter circle, we've got here is F sub V, and it is a distance of 1 meter from the edge. 1 meter. Just by inspection, we can tell that it's going to be at the center. It's symmetrical. Now W, the location of this force, we want to find out what is the distance here. And we can find that with the centroid of a quarter circle. The formula for the centroid of a quarter circle is 4r divided by 3 pi. That is 4, the radius is 2 meters, divided by 3 pi, and that is 0.8488 meters. So that distance is 0.8488 meters. And it makes sense that it's less than 1 meter. Do you have a question, Michelle? No. Okay. It makes sense that it's less than 1 meter. It's not going to be at the center. It's going to be a little bit further to the left because of all this area being missing. That shifts the center of area towards the left. So that tells us where this F, we called it W, is here. And so we could come up with like an average, a weighted average of where that is located. You know, we've got F sub V was the greater of the two. F sub V was 109. Well, wait, that was the total. F sub V was actually 78.48. 78.48 kilonewtons. And W was 26. No, it was 30, right? 30.819 kilonewtons. All right. So what we can do is just find out the weighted average of where that line of action is going to be for the two forces together. There's going to be F sub V acting at a distance of 1 meter plus W acting at a distance of 0.8488 meters. And then we divide by F sub V plus W. So if we multiply W, which was 30.819, and F sub V was 78.48, and divide it by the sum of the two is 109.3. All of that together gives us that the location of the two forces together is 0.957 meters from the edge. The edge was from CA, and so the force is located not quite a meter away from that surface CA. We can refer to that as like an XCP. You remember we had YCP that was talking about the distance to the center of pressure from the surface down to the location of the force. This is in a sense a horizontal location to the center of the pressure relative to that AC being the datum that we were measuring from. Any questions so far?
Yeah.
Yeah.
For your area is 2 meters cubed. Where do you get 2 meters cubed from? I still don't get that.
2 meters squared?
Yeah, not on the very top.
Here.
Yes.
Okay. The best way to explain it is here's a rectangle. Now, we know that this is a curved gate. So it's basically a curved gate like this, a quarter circle. Maybe I should just do it the other way. Got a quarter circle, So kind of like this. Now if I turn it towards you, what does that shape look like if you're just considering the vertical component? It just looks like a rectangle. Like if you're just looking at it right now, it looks like a rectangle. If you're looking at it either from the front or from the back. The vertical component of this curved surface is a rectangle. So here we had a curved surface and its vertical component is 2 meters and it's 1 meter into the page. So we're saying if we have this curved surface, then its width is 1 and its height is 2. Yeah. Yeah. Yes. I think that formula is in your appendix. It's just a generalized formula for the centroid for a quarter circle. Other questions? So here it's showing the formula for the centroid of a quarter circle, 4/3 4r divided by 3 pi, area of a quarter circle. Now, we found that the vertical component was 109.3, the horizontal was 98.1, the resultant 146.9, and we can find the angle that makes, the equivalent angle, just by the tangent of the ratio of the two. So, you know, we can find out what direction it's acting in based on that. This is where we're going to head in class on Tuesday, is taking a look at the force required to open this gate. Now, I don't think this is in your slides, right? But being able to visualize what a curved surface looks like is really the key to solving problems like this, is just thinking, what is the vertical component of a curved surface look like? And so take, for example, if you had a submarine with a window on it, the kind of window that you could actually stick your head and look around. So if you have a vertical surface and then a dome sticking out like that, you know, it's a hemisphere, half okay, not the best artist, but if you have half of a sphere, then what that's going to look like, the projection of it, if you've got the light shining, the projection of it is going to be a circle, basically. Those are the two surfaces that you're going to have projections of, is you know, a hemisphere, or I think there's a problem in the coming homework assignment where you've got like a circular screw that's going in, and they're having to find out the what pressure is acting on a gasket. A circle is the vertical projection of a sphere, and a rectangle is the vertical projection of a curved gate, like the example that we worked today. So we'll get to that example in class on Tuesday. Let's just take one last look at these announcements. That you've got the homework assignment 3B due in class on Tuesday, and also the Water Gems lab activity due on Tuesday. So if you're not able to install Water Gems on your own PC, for now the easiest thing is just to use the lab computers. We'll be using Water Gems a lot in hydraulic engineering next semester, but this semester we're just going to have 2 very short activities, and so it's not worth doing a lot of technical support and trying to get it, forcing it to work at this point, because they'll probably issue an updated version of the program between now and then anyway. So that's it. I'll see you next Tuesday.